Why would you have smelled it better when you rubbed it on your hands versus out of the little hole?
Most surface area.
Bingo.
Oh, wait.
Yep. Alrighty, cool. Let's get started. So we are on the final third of thermochemistry. I think by my plan, from what I think you guys can handle today, we will be able to get more than halfway through this final third. So this last question is all about enthalpy. So if you guys remember structure and bonding last year, you had your calculation question, and that was enthalpy related. So your enthalpy question, is it doing that flashy thing? Stop doing that. All right. So when we're talking about enthalpy, what do you guys remember from that? What is enthalpy?
The release of heat.
Not just the release of heat, but also absorption. Yeah. So this here is talking about the heat transfer in a chemical reaction. So heat transfer in a reaction. With that enthalpy, be mindful that it does vary depending on the pressure and the temperature. So when we're talking about enthalpy in these examples, they're in standard conditions. So you guys remember what standard conditions are? No, it's okay if you don't, because it's just so that way you guys understand. So it is 1 atmosphere pressure, which is what we're in, and it's also 25 degrees Celsius. 1 atmosphere of pressure, which is 100 kilopascals, and at 25 degrees Celsius. So just something that I'm adding because you'll often see them mention that it's at standard conditions or at 25 degrees because obviously the temperature would affect what's happening because we know that at different temperatures molecules are moving at different rates and that could influence energy and things like that. Cool. With enthalpy, we talked about Calvin, you said what, energy release or heat release? So do you remember what term we use for a reaction that releases heat?
Exothermic.
Bingo, exothermic. And then the other one is? Endothermic. So we have those terminologies, exothermic, which is releasing energy. Energy. When you guys are looking at the graph, if you ever see an exothermic reaction, actually let's go through things that we can use to help identify if we have a exothermic reaction. So do you guys remember the delta H? Mm-hmm. So delta H is your change in enthalpy. For an exothermic reaction, would that number be positive or negative? Do you remember? Mm-hmm. You got a 50-50 chance of getting it right.
Positive.
Not negative. So if I see a negative number when I have a delta H, that tells me it's an exothermic reaction. If I felt a test tube that was exothermic, what would it feel like? Hot or cold? Hot, because it's releasing energy. I'm trying to think what else I want to tell you. All right. When we are thinking about exothermic reaction, remember we are comparing and contrasting the energy required to break all the bonds versus the energy that's released when we make the new bonds. Does this ring a bell or should I write that down?
Maybe.
Write it down?
Yeah.
Okay. So as a little side note, I'll put it down a little lower. So we have reactants, and then we have products in our equation, right? So with the reactants, we need to break the bonds. And with the products, we need to make new bonds. When we break bonds, breaking bonds will require energy because that makes sense because I'm trying to force things apart. I was trying to think, there's an analogy that I use. Let me just plug in my computer so it doesn't go dim and lock us out. It just did it. Here we go. All right. The way I like to think of, I'll do the other one and then I'll give you my analogy. So products then, when I make the new bonds, that is going to release energy. The analogy that I like to use is you think about two magnets that are sticking together. The magnets and that magnetic bond, when it forms, it forms easily, and it's going to release some sound energy because you hear the magnets clack together. And then when you try to break that magnetic bond, you're pulling it apart, and that's requiring energy. So that's the analogy I like to use because people tend to get them backwards for some reason because they think if I break stuff, that it's releasing it. And it's like, no, you're putting in energy to break it apart. What we can then do is compare and contrast how much energy is required versus how much energy is being released. So in an exothermic reaction, the energies that are being made by new bonds is greater than the energy required to break all those bonds. So bond making energy is greater than the bond breaking energy.
Is it opposite for the other?
Yeah, basically. Yeah. So that's what makes it exothermic. So I'm releasing more energy than I need to put input into it. The other thing you guys probably would have seen are the little diagrams as well with the endothermic and exothermic reactions. And basically you have, and it could pop up again. So the reason why I like to revise the level 2 stuff is that level 2 stuff is fair game. So you guys have seen this time, and that's energy. And you see things labeled as that's my reactants, and that's my products.
Yeah.
And then this difference here, let me grab another color. That's the energy released. Yeah? And then that little hump that we have here, that's the activation energy. Are we good with that? All right, keep going. All right. So basically, endothermic is the opposite. So when we talk about endothermic reactions, we're talking about absorbing energy. If I was thinking about my delta H, what would my delta H be?
Positive.
Positive number. What else? How would it feel? Cold. That's how the ice packs work. Feels colds. And then if I was comparing bond making versus bond breaking, which one would be better? Bond breaking. So we have bond making energy. In this case, we change the sign so that way it's the bond breaking. So I need to put quite a lot of energy in there. And then the last thing is just what would that energy diagram look like. So in this case, what the energy diagram would look like is my reactants would be lower. I still have my activation energy, and then my products would be up there. And then this section here is representing the energy absorbed. Yeah, silly birds. Do you guys remember about catalysts? You talk about them in bio. So what would a catalyst do in this context, do you know? In both contexts, I should say. It speeds up the reaction, but why does it do that?
Oh, does it,
I thought you were going. Yeah, it lowers that activation energy.
Oh.
So that's why it speeds it up. So if I lower the activation energy, I then don't need as much energy to do that reaction, and thus I can use that energy for other reactions, speeding up the whole process. It has never occurred to you why. Okay, that's okay.
I just feel like you just add a catalyst and makes it get it out. the way.
Yeah, so the catalyst is providing some sort of way to reduce that activation energy. All right, are we good so far? Can I give you some more vocab? So this is the vocab all from last year. Now I gotta give you some new stuff. It's not that bad. I think it's cool. And I'll talk Hess's Law today too, I think. Because I think you guys can handle that much. All right, what questions do you have so far? Keep going?
Yeah.
Okay. Don't worry, I will scan this and this is being recorded. Okay, so we're gonna learn some new things today about that delta H. So if you guys remember so far, we've talked about some of the new delta H's. You've had the delta H of, now I gotta remember, vaporization.
Vapor fusion.
And then fusion was the other thing.
And what is the ACB?
Sublimation.
So,
So that's going straight from solid to gas. So we've talked about some new delta H's, and that's talking about the energy required to do those things. So this one here is talking about liquid to gas. Did not plan that through. This one here is talking about solid to liquid. This one is solid to gas. I don't know why I'm writing out gas and not the other ones. Cool. So those are the ones we've talked about so far, and we've talked about them in the context of the molecules and their phase changes and things like that. And why are they always endothermic? Well, it's always going to require energy to break the intermolecular forces. So the new ones that we're talking about, there are two new ones. The first one is your delta FH. Should be doing those little dots. Put it on the other shade. So delta F, don't confuse this one with this one because they mean two different things, because chemistry is real nice like that. This one is talking about the enthalpy of formation. What do you guys think formation means? What does form mean if I want to form something? Yeah, to make it. So I'm literally, this is the enthalpy of making stuff. So for example, if I have water, H2O, we're talking about the enthalpy required to make water. Now, when we are doing this, there's some things you guys got to keep in mind. First off, you are always setting a formation equation with the product being 1. So always 1 mole. So you know how you guys are used to balancing equations and you just kind of just do it? This case, you have a rule, and that rule states this guy has to be 1. Everybody else is in reference to that one. That means now that we can have fractions in front of our molecules, and that's okay. All right, so if I only had 1 mole of water being formed, how many hydrogens? Oh, sorry, I should backtrack. Enthalpy of formation, when we're talking about formation, we're talking about formation from its elements. So it's compounds from elements. So if I was looking at this guy over here, how many hydrogens would I have? Or what would I get as my hydrogen? Would I have just plain H, or would I have H2?
H2.
H2, because that's how we see it in the molecular form. What's the other thing I would need?
Oxygen.
Oxygen. And I'll put in some states, because states are good. All right. Do I need to have a coefficient number in front of the hydrogen? No. What about the oxygen?
Yes.
Yeah. What number would I put in front? Knowing now that we can use fractions. Half. Or 0.5. Because if I did 2 times a half, I get 1. And that's how I'm getting the water. So that's what formation equations look like. And you'd also get your delta FH, which would be negative 286 kilojoules per mole. Kind of squish there. So is that formation exothermic or endothermic? Exo, it's going to be releasing energy. Here's a nice little trick question. You see how this one's, and I love this question, that's why I'm saying it. This is being formed in the liquid form. If I form this in the gas form, would I expect this number to be release more energy or less energy? If this was a gas instead of a liquid. 50-50 chance of getting it right.
Can someone else go? I got that one.
So would this release more or less energy?
Or make it a liquid.
If this, instead of being a gas, or sorry, instead of being a liquid, was a gas.
More energy.
No. Not your day, Hannah. It's going to be less energy. So just be mindful that if, this is a common question. If H2O was in the gas state instead of liquid state, less energy would be released. And I'm just making a note of this because this is a very common question they ask. So the reason why is because this energy, some of it needs to be used to break the intermolecular bonds for this the phase change. That's why it's less. So you'd expect a more positive number. So it might be like negative 250. So it's not as releasing as much energy. All right, we okay with that? So that's the first thing that we have. Do you guys want me to write down some practice problems or just keep going?
Maybe like one.
One? Okay. Do you want a hard one or an easy one?
Medium.
Medium? Okay. I'm just trying to think which one's a medium one. All right, here's another example. Formation of sodium chloride. Yep, so Na and Cl are my two elements.
Yeah.
Would I just have pure Cl or would I normally have it as a molecule?
Would you have it as isn't it gas?
It is a
Because
gas.
it's so Cl2 because it's on the
Yeah.
yeah.
And then sodium would be a solid.
Yeah.
And then is there anything I need to do to balance it?
The half.
The half again.
Yeah.
Yeah? So just be mindful of different things. You guys are used to seeing a lot of your gases as twos. So like nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Other stuff you tend to see just as the element on its own like this. The metals would be like this. Copper would be like that. Sulfur would be like that as well. All right, next bit. Move a new page. All right, so the next thing that we are then thinking about is another type of reaction, and I'm gonna do this one in red because it makes sense, and it's the enthalpy of combustion. So what do you guys think that means?
What is it for?
Enthalpy of combustion is what that one is. That's what the C is for.
Isn't that like fire?
It is fire. It's related to combustion. It's related to that like burning stuff.
Yeah.
Now, what's something that we need in order to burn things?
Yeah.
You need, well, it's releasing heat. Stop flickering. If I had a fire in this room, what would I do to put it out?
Oxygen?
Okay.
Thank you, oxygen. So you need oxygen to burn stuff.
I know.
Got one finally. All right. So the way this one works is we're thinking about combusting things in oxygen. So it can be any sort of compound plus oxygen to burn it. I'm going to use the example of methanol because we know that burns. So CH3OH, and we know we need oxygen gas to burn it. And then when we burn things, you are then combining them together with the oxygen. So I would have, in this case, I have carbon, hydrogen, and oxygen. Now, oxygen I'm not worried about, but I am worried about the carbon and the hydrogen. So what would I get if I burnt, or what would I get as a combination, do you think, with carbon and oxygen?
Oh, carbon dioxide.
Carbon dioxide.
Yeah.
And what do you think I would get with the hydrogen?
Hydrogen.
Hydrogen and oxygen, what would happen?
Hydrogen. Water. Oh.
Yeah, just water.
Oh, okay.
Easy peasy. Yeah? So when you're burning things, you're just thinking about, you know, how do I combine that element with oxygen? Okay?
Okay.
Again, you have the same problem coming through. This has to be 1 mole for these combustion reactions. So this is set to 1 mole. So everything gets balanced against that. The way I would do this is I would first balance everything else, and the last thing I balance is the oxygen, because I need to figure out everybody else before I figure out the oxygen. So if I look, I have 1 carbon here, 1 carbon here, that's balanced, no coefficients in front. I have 4 hydrogens here, and I only have 2 here. So 2 in front. And then last step is I need to go through and count oxygens and figure out how many oxygens I need to add. That's 1, 2, 3, 4. Now I already have 1 from the methanol, so I have to factor in that I don't need 4, I only need 3. So that's going to be 1.5. Do you guys want to see the math behind how I know it's 1.5?
Yeah.
Because 1.5 times 2 equals 3. Cool. And that's how I got that. So those are my combustion ones. Do you guys need an example that you want to try? Okay. How about you guys try that methane, burning methane.
So will it always be plus O2?
Yep, because combustion. All right, so what else would I get?
So you get carbon dioxide.
And then I would get,
GH2.
you would not, because remember with combustion, you're always combining the oxygen with, so you'd get 2 H2Os.
Oh, okay.
Yeah.
Oh.
And then how many oxygens do I need?
You need 2 on.
2, 4, 2, another 2. Cool? Easy peasy? All right. Another common question that they often ask is why would the combustion energy equal the formation energy? So I'll give you guys an example. They love to use stuff like water. So if I do the formation of water, we've already done that here. What would the equation be for the, so this is for H2O. What would the combustion equation be? So for H2O.
It would just be H2 plus.
Is it H2O? Oh, sorry, the combustion of hydrogen. So the combustion of hydrogen and the formation of water. Why is that the same equation, or why is that the same enthalpy value?
Aren't you forming water with the?
Yeah,
Yeah.
that's what you're saying. So with the combustion of hydrogen, it's the exact same equation as the formation of water.
Yeah. Because it's the element.
Yeah. So that's why those two numbers are the same. Same equation.
So would you like show the equation and then say it's the same?
Yeah, same equation. The last thing I probably need to talk to you guys about is what would the enthalpy formation of elements be? So we talked about compounds. What about elements? How do I do an equation with an element?
What?
Exactly. You won't be able to do it. It's going to be 0. So if I have any formation of elements, it's just 0.
Oh, that was a trick.
It was a trick question. Yeah, you guys were stumped. You're like, I thought I was getting it up to this point. All right, cool. So that's all the vocabulary. We've been chatting for about a half hour. Do you guys want me to start doing some Hess's Law, or do you want me to put that for next week? Hess's Law is your vote. Anybody else? You guys happy to have some more information tossed at you? Or is this enough?
But like, if you guys want.
We've had one voice. Anybody else want to share their opinion?
I kind of don't. I don't know what you guys think. What do you want to do?
Where will you teach it next week?
Yeah, I'll just move to next week.
I won't be here next week Friday, so I'll put it in
So you'd rather do it now?
Oh, it's what?
I'll send it to you.
How do people think?
Should we have send it to Yeah, I'll send it and then I'll teach it.
Yeah, or the other option is we can do it next week on the Friday, or we can do it like before or after school kind of thing.
We don't know.
It's up to you.
Oh no, we won't do it. The dish can just submit to me.
Okay.
And I'll do the credit points.
All right, so the majority says no? Okay. Cool, we'll just leave it here for today. You guys can practice this. Let me tell you what SciPad pages work for that.
Oh, yeah.
So,
Oh, my God.
let's see. Thermal principles. I think it's 90. Let's see.
Tommy, I do
All right, if you guys want to practice these equations, it would be 90, 91. And I think that's it for now, because I haven't taught you Hess's Law. I can teach you guys part of Hess's Law if you want.
What is Hess's Law?
That's when we can manipulate equations to figure out enthalpy. It's cool. It's really therapeutic to do.
It's really satisfying.
Huh?
It's really satisfying.
It is really satisfying as a thing. Yeah, it's a really, it's just fun.
So like you can calculate the energy that was needed for the.
So if you don't know the enthalpy of a reaction, but you know the enthalpy of other reactions, you can manipulate the equations and thus be able to combine them together to then figure out the one that you don't know.
Oh.
It's really therapeutic to work through.
So like if you know the formation, like is that
Yeah. So you're basically combining multiple equations together and like flipping them around or multiplying them and then putting them all together. It's very similar to like the redox equations and how you do those steps.
Oh, I like doing that.
So, but I can teach you some of it if you guys want to know some of it. That gives you more SciPad pages to do.
you're like
You're like, I like.
Like a hot day.
Or should I just leave it all to next week?
Yeah.
Next week? Okay. Cool. I'll stop
Skin
there.
off your back.
Huh?
No skin off your back.
So I think I said like 90, 91 are the 2 pages that do this equation practice. And then I think there's probably some pages in there to do revision for enthalpy from last year.
Yeah.
I'll post it on Google Classroom.
Yeah, it's really.
All right. I'll stop the recording.